Are vectors going to be on it?
Yes.
No, probably shouldn't do it today.
Dot product. Okay. A dot product is our way of multiplying two vectors. If we have the vector u and the vector v, then our dot product is the scalar. Scalar means what?
Absolute
Yes,
values.
just a number. Okay. The vertical components multiplied together plus the horizontal components multiplied together plus the vertical components multiplied together. So the product of the horizontal components plus the product of the vertical components.
So it's almost like a matrix.
No.
Shot.
Matrices are row times column, and I really can't relate that here.
Well, you have like a row of, you have 2 rows and 4 columns.
Yeah, no. It's like 1 row and 2 columns, or 2 columns and 1 row. However,
It
that
seems
works.
like it's related.
I was thinking the same thing.
There's some columns.
Cabby.
What?
No, you don't kid
No,
yourself.
what do you mean? You don't know my mind.
This is true. I think it's better that way. Okay, properties. Unlike matrix multiplication, the dot product is commutative.
Oh, is that Hey, that's what my little brother's learning, like 6th grade, 7th grade math.
Do you help him?
Occasionally.
There's something.
It's tough.
Okay, the dot product is distributive.
That's a W. If you smush your U and V together, it looks like another W.
Probably. Now, the dot product is like a multiplication. If you had 2 times 3 times 4, is that the same thing as 6 times 8? No. Either 2 times 12
That's like double.
or 6 times 4 or 8 times 3.
24.
Okay.
Good job, Kathy.
So if you have a scalar multiplied to a dot product, you can either multiply the scalar to u and then dot v, or u dot cd. What is u dotted with the 0 vector? Ah, good job. The limit?
Yeah, we need a limit in there.
Well, I assume the vector
You take
has
that limit of a
value
vector.
0, 0 times.
The limit as your first.
V dot v.
W. V squared. Just.
V.
It would not be v squared, but
Was he close
almost.
with W?
No, he was closer.
2v squared.
What do you say?
V1 squared plus V2 squared.
Wait, isn't
Okay.
V the same
V
thing?
sub 1 squared.
So the horizontal component squared plus the vertical component squared, and what does that look like? Without the square root. So it's magnitude squared.
Uh-huh.
Okay? So,
Sorry.
let's say we have a vector v and a vector u. Okay? We can actually find the angle in between two vectors. Okay? Now, what? No,
Well, you
like,
can find that too.
Oh, the angle. Oh, I
okay. We could find the bisectors,
yeah.
but it's actually going to find the closest angle. So technically, there's two different angles between u and v, but it's always going to find the one between 0 and 180. Okay. What would an angle of 0 mean?
They're the same thing.
They're the same
You-
direction. What would an angle of 180 mean? Opposite direction. In both cases, they would be parallel. Okay? So, in order to find this, we would take the cosine of theta is equal to u dot v over magnitude of u times the magnitude of v.
They essentially just the inverse cosine.
Yes. Okay. Now we could actually prove this by using the law of cosines. What would this vector be right here?
Would that be would that be u times v? Yeah.
Okay. And we can use the law of cosines to do that, but I'm not going to take the time.
Does that mean V is the long side?
That would be.
No, it's that one. Okay. But we're not going to worry about that today. I'm going to give you two vectors.
Okie dokie.
Okay? So if I'm going to find the angle between these, we need two things. First of all, what is the dot product? Right? 2 times 1, negative 3 times negative 2. What is the magnitude of u? Square root of 2 squared plus negative 3 squared.
Uh-huh.
Magnitude of v. So we have the cosine of our angle is 8 over radical 13 times radical 5. Or just radical 65. In degrees, how would you give that to me?
Whoa, in degrees?
I know.
I haven't done that this class for months.
What did I do? I don't have
They were in degrees 7. That makes sense.
How many degrees? 7 point.
1, 2.
Nice decimal.
Oh, no, it's like
No, I know, you guys agree, but I like 0.125. That's nice.
It's like an 8.
Yeah.
Yeah, that's good.
Now, how could you tell if, lost my train of thought. How could you tell if two vectors are perpendicular?
If their angle is negative,
Their slope
or their
are-
cosine is equal.
If you
Cosine
do
would need to be
zero,
0, right? So first of all, perpendicular vectors, what do we call those?
Normal. No.
Orthogonal.
Oh, yeah, I remember that. No.
Wait, are you serious? Okay. Just want to make sure.
Orthogonal means perpendicular vectors. Okay, so Nathan said the cosine needs to be 0. So essentially, what needs to be 0?
In other words, u needs to be 0.
Yeah.
What needs to be 0? What the dot product?
Okay.
So if the dot product equals 0, then we know we have orthogonal vectors. So please tell me what's true about the vectors 218 and 3/2 negative 1/6.
They're orthogonal.
Are you sure?
No.
If you're using this example, then
I'm sure
obviously
now.
they must be.
Nate?
3 is 0. Was negative.
Okay, what's 2 times 3/2?
3, and then the other one is negative 3. And when you add them together, it works out nice.
So we have orthogonal vectors. Okay. Okay. Talk about projections.
Projections. Those are fun.
Not like.
Like the projector projections.
They have angles and stuff.
I'd say yes.
I don't know.
What about?
Okay. V and W are two non-zero vectors. Okay? Then the projection of V onto W is the dot product over the magnitude squared times W.
What do we use projections? So it's like
We're going to use it to help us find work.
Is that dot W or just W?
Well, let's see. It's going to be a scalar times W. So it's going to be, I mean, I guess if you want me to just write it as W, right? Because the dot product is a scalar, the magnitude is a scalar, so this is going to be a scalar times W. So you're going to end up with a new vector representing this blue right here. So this is the projection of V onto W. Okay, what does it kind of look like? To me, it kind of looks like it's shadow.
If the sun is directly overhead. At noon,
At noon, the shadow at noon. Okay.
it is a clock.
Back
It is a
from the
clock
city hall.
with the third.
Well, second sun.
Oh, brilliant.
What time is it? 3:15.
15.
3:15. No. 3:05. 3:07. And 15 seconds.
It's 10 to 3.
We're talking about the one there.
It's a clock. You see those three hands? Minute, hours, and seconds.
Okay. Now, we can talk about the decomposition, okay, where we can talk about parallel and perpendicular, okay? So what's true about the projection of W onto V? Excuse me, V onto W. It is what compared to W? Parallel, okay? If V and W had angles, so like if this was W and this was V, then our projection would be over here. Okay. Projection of V on W. Okay. Okay.
Basically like.
So, right. So I'm going to call this, instead of writing the projection every time, I'm going to call it V1. So V1 is parallel to W. Okay? Now, we can actually find a perpendicular vector very easily. I'm going to call it V2. These would be after the square. How would we find that one? Any ideas?
That is a projection. So the perpendicular vector with W is going to make its dot product 0.
What I want you to imagine is this under right here. What's going to be true about V1 and V2?
V1 squared plus V.
Those are going to be the components.
Okay. So this is basically, if I basically take V1 and V2, they add together to be V. See that? Like if I move V2 right here,
Then you can do that.
tail to head addition, right? This vector plus this vector, we connect them, and there's our sum, right? So if they add to B together, then we can say that V2 is B minus V1. That's our perpendicular vector. And so V2 is perpendicular to W. So we're doing an example here. Of the vector v, which is 2I plus j, and the vector w, which is I plus j. What would these look like? There's v.
Projection V on the W or W on
Hmm?
you want projection V on the W, W on the
We're going to find the projection of v on the w.
You can already write it like that. Proj sub WV.
Well, the projection of v on the w.
That's like logarithms. You have the log, you have the base, you have the...
I mean, it looks like that, yeah.
So
Okay.
is this one like outputs?
Huh? So say this one was v, right? And this one was w. Yeah. So it's kind of like that. Okay. So what do we need to do?
Dot product.
We need the dot product, so 2 plus 1 over magnitude of w squared. What is the magnitude of w? Square root of 2 squared. And then we multiply it by w. So we have 3/2 times w, right? Okay. And then we will, the decomposition. Okay, so this is our V1. This is the one, this is the projection that would be parallel. Now let's find that piece perpendicular. How do we find that? V minus the projection, right? So we need to take 2I plus j and subtract 3/2 I plus 3/2 j to get 1/2 I minus 1/2 j. Right? This is where it gets interesting. You already thought it was interesting? Okay, well now let's use it for some physics. Now, do you guys talk about projections in physics?
No, but I understand exactly where you're going.
Exactly.
Forces for work.
Okay, we're going to talk about forces first. So a 600-pound boat sits on a ramp, inclined at a nice 30 degrees. What is the force required to keep it from rolling?
Wait, is that what we're talking about?
Is it on wheels?
No.
Well,
Is there friction? In physics, we're always told to ignore it.
ignore friction.
You are?
Yeah, like all the time.
And then there,
Yeah.
unless there's
Until we learn how to find
Give
friction.
Marshall a month. You go.
No, we got there. I think. I'm not really sure. I'm just really sure.
Yes, they do.
Okay. So what's happening?
There's a boat on the ramp.
Okay,
Just gravity.
okay, so where's gravity pulling from?
Down.
That way. But you can also make
Okay.
Oh, so you need
Triangle.
component of that.
perpendicular to it, and then
The force required to keep it is gonna be
Okay, so,
So I guess we have talked about the projections, but we did it in a weird roundabout, we just didn't talk about the words. But we found perpendicular and parallel components of that.
okay. So let's talk about the force of the boat. What is this vector?
600
times 32.
straight down, it's 600 times. So much
Oh.
both ways.
I thought that was in
Well, if you want to.
So negative 600 up, because it's pulling down, right?
How's this force?
Okay, let's talk about this vector right here. How do I find each component?
Trigonometry.
Okay,
what are you trying to find?
this vector.
Oh, wait,
You know, if you make it
trying
into a J.
Yeah, I don't know why I wrote on. That's why you guys pay attention.
Yes.
Okay.
She's just
So V. So horizontal component, we look at what of the angle? Cosine. What's cosine of 30?
33 or 2.
Sine of 30?
or not.
We'll just make it a unit vector. Okay. So now, what are we looking for as far as the force keeping it from rolling?
The B is the opposite of the parallel component of gravity.
Okay. How about in terms that we've been talking about?
W.
Projection of gravity onto the B.
The projection of F on V. Okay. Hmm?
Cheers.
Yep, and Andrew. So the projection of F onto V. So first we need the dot product.
Oh.
0 plus negative 300 over magnitude squared of V. What is the magnitude?
Wait a second. No. Hey. Is that the final answer?
No.
Wait.
Times speed. Because we get a vector out of the
Okay,
field.
yeah.
So we have negative 300 times the vector radical 3 halves I plus 1/2 J. So let me ask you, what is the force to keep it from rolling? What are you looking for? The magnitude. What is the magnitude of this projection?
300.
Marsh ones actually we got all this fun part.
That's the time.
Got excited. I have a working example now. Okay. How is it 300?
Because
Well, if you think about it, this is a vector with magnitude 1 times negative 300. It's going to have a magnitude of 300.
If you want to be precise, it's technically 300.00000000001.
No, precisely 300.
So why do I have 0.00006? Probably.
Well, she's gonna want to see the calculator.
do you have to see the calculator? Because I got 300 with Marsh.
And what is Marsh now?
You drew a little triangle.
You did projections. You got projections.
And you draw like a little thing here. And here. Angle. And this one. It's the same. That's 30 degrees. And you just find that angle. And since this is an equilibrium, the force of gravity going down has equal force going up. And that's 300.
And that angle is always equal to the angle of the other triangle because geometry.
Yes.
So that would be 30 degrees as well.
Yes. It works. Like every time.
Every time. Okay.
It does.
See that in physics 1? All these studs in physics 2 didn't know that.
Because that's how it works.
Be unlike you.
How do you find work?
4 times its placement.
Okay. So it's always nice when our force is in the direction of our movement.
Yes, it's generally.
Well, you know, this totally lines up with
This
physics 1.
will be exactly.
What about if our movement is different than our force?
Which that
Components.
Which is perpendicular.
Break it up into components.
We could do it.
Actually, we've done this too in physics. We tend to do geometry.
I know. Would you like to do it the vector mode?
I guess.
Which is easier.
I really like the old way.
The old way.
You only have to know like algebra 2 to do it the old way.
It's true. Let's do that. Force of 15 pounds. Pulls a wagon. 30 feet.
Three the wheels on the
At an angle of 30 degrees with the horizontal.
Oh.
Now we
Those are my two children in the wagon.
Very
They
lovely.
like on.
Very lovely.
Or on.
Maybe those are their arms holding onto the sides and you can't see their legs because they're sitting down.
Okay, that works too.
Okay.
Does the projection of force here give us a work? No, we give us a force.
Hmm?
I'm trying to think of, because I was thinking because we're going to project force.
Well, you could project force onto your movement and then take the dot product of those two. Okay, so you could take the projection of your force onto, let's say this is PQ, onto PQ. Take the magnitude and multiply that by the magnitude of your direction. Okay, or we could do this. We have 15 pounds of force at a 30-degree angle. And we're pulling it 30 feet. Okay, so let's talk about this vector right here. What's our force vector?
Parallel components.
So 15 times the cosine of 30 plus 15 times the sine of 30, j, which is what?
This is after the parallel.
This is f. Okay? Force times displacement. So we can just take force times our displacement vector. What's our displacement vector? It's 39. So force times displacement.
So the dot product.
Yes. So 15 radical 3 halves times 30 plus, it doesn't matter, times 0. And our work is what?
25 squared root. That's 30 minutes.
That's the pre-calc way. I think it's easier than finding the magnitudes and multiplying them. But it's the same thing. Okay, so your homework that you're actually going to do because you have a quiz tomorrow.
Yes.
Your quiz tomorrow will cover parametric equations, parametric derivatives, length of a path, speed of a particle, vectors. No review, just your homework.
I got confused on this thing for one of them.
Okay. Let me go ahead and stop this here.